Hi, welcome back. In this video, we're going to look at system properties memoryless and causality. And I do want to point out that sometimes these system properties can get a little bit abstract. So I do want to encourage you to look at the example videos that will follow this video in the sequence, but we will look at some basic examples in this video as well. So what are memory and causality? Let's have a look. So I've got some definitions up here for you. Memoryless. A system is memoryless if for every value of time, the output at that time is dependent only on the input at that same time. Okay, so that's a mouthful, but let's take as an example the simplest system, which is the true bypass or the identity system. So let's say we have a continuous time system with input x of t and output y of t. And if this is an identity system, then the input is equal to the output. Now, let's say I want to know what the output is at t equals 1. So what is the output at t equals 1? Well, according to the identity system, that is, put a colon there because we're considering t equals 1, y of 1 is equal to the input at 1 second, right? So whatever I get out right now at 1 second is equal to the input right now at 1 second. And okay, so that covers this part. The output at 1 second is dependent only on the input at 1 second. But that has to be true for every value of time. Well, let's try another value of time. How about y of 2? Okay, the output at 2 seconds, or the output at 2 units of time, is the input at 2 units of time. Yeah, so you can see where we're going with this. This true bypass system, or this identity system, is memoryless because the output at time step t only depends on the input at time step t. That should seem obvious, but let's consider a more advanced system, I guess. Let's consider a delay. I'm not going to draw the box now. A delay in discrete time. Okay, so here's another example. If I want to know the output, let's say at n equals 0, okay, at time step 0, then according to the delay, I need to know what the input was at time step -1. That is, I need to know what the input was 1 sample ago. Yeah, because this is a delay. Well, according to our definition of memoryless, the output has to depend only on the input at that same time. But right now we're asking for the output at 0, and we need the input 1 sample ago. So we conclude then that a delay is not memoryless. All right, this one was memoryless. And see, when you disprove a property, all you have to do is give one counterexample. Y of 0 is equal to x of -1. And you say, well, because I need the input at -1 to get the output at 0, yeah, that's not memoryless. To prove the property, though, you have to show that it's true for all values of time. And in this case, you can say, yeah, well, the output definition, right, the output y of t, I only need x of t, so that's clearly memoryless. Okay, what about a time advancement? where the output is the input advanced by 1 unit? Well, again, if I plug in a value of n, let's say 0, I need the input in the future. I need the input 1 unit in the future. Okay, well, again, because the output at time 0 depends on the input at something else other than time 0, this is not memoryless. So be careful here. Memory is usually thought of something that happened in the past. But for our definition of memoryless, it can happen in the future as well and still not be memoryless. And let's take another example. How about a continuous time proportional block? So y of t is equal to 2 times x of t. Okay, well, you see right away from the definition of y of t only requires x of t. It does not require x of t minus 1 or x of t over 2 or anything like that. So you can plug in values of t here, but what you'll see is that you'll always get that the y of whatever value of t you plugged in is twice x of whatever value of t you plugged in. That is to say, the output right now only depends on the input right now. So this is memoryless. Again, some more sophisticated examples will be covered in an example video later in the sequence. Now, causality. A system is causal if the output at every time depends on input values only at the present and past times. So this is like memoryless, but we're allowing past times as well. So let's look at the very first system we did, which was the identity system. Does the output depend only on the current input or past inputs? And yeah, it does. It depends on the current input. So that's fine. It has to depend on the present or the past, but not the future. So this is memoryless and causal. Okay, let's consider our second example where we're analyzing a delay by 1 unit. So if I want the output right now, I have to look 1 unit in the past. So is that causal? It is causal. It is causal because the output y depends on the input, now or in the past, but not in the future. So this is causal. And the third example we looked at was an advancement of 1 unit. So is this causal? Y of 0 depends on x of 1. So no, this is not causal because the output depends on the future values of input. So we would say not causal. And the last example was an amplifier or a proportional of 2. So the output is twice the input. So is that causal? Yes, because the output at time t depends only on the input at time t, the present time, not the future. So this is causal. So what can you say about the relationship between memoryless and causal? Pause the video if you want to think about it, but the answer is that if memoryless so memoryless implies causality, right? Because if a system is memoryless, then it only depends on the present values of the input. So by definition, that's also causal because causal is a little bit looser of a definition, where the output only depends on the present and the past inputs. And similarly, we can turn that around and we can say, if not causal. So if we knew a system was not causal, then that must mean the output depends on the future of the input. So by definition, that means not memoryless. Well, I hope that makes sense. And so let's continue with our system properties. And again, we'll look at some more examples in later videos.